Today, we're digging into the story of a programming language that did something everyone thought was impossible. It's a story that starts with a simple, everyday annoyance and, believe it or not, ends up changing the entire digital world. It sounds like a riddle, right? But the answer is actually a fascinating story about a fundamental rule in the world of computing, a rule everyone thought was unbreakable for nearly 50 years. It's a tale of speed, safety, and a quiet revolution in how we build our most important software. Okay, so to really get this, we have to understand the core problem that basically defined software for decades. You see, for the engineers building everything from your operating system to your web browser, there was always a choice they had to make, a fundamental trade-off they just couldn't escape. For half a century, this was the deal. On one hand, you could choose languages like C and C++ for raw, bare metal speed. This gave you incredible power and control, but it was also incredibly dangerous. On the other hand, you could go with languages like Java and Python. They gave you a safety net, managing all the tricky memory stuff for you. But that safety always came at a cost. It slowed things down. So you could have speed or you could have safety. You just couldn't have both. And this compromise, it had staggering, real-world consequences. 70%, that's a huge number. And get this, it wasn't because of bad programmers, not at all. It was a systemic flaw in the tools themselves. The very languages we use to build our most critical software were inherently unsafe, putting a massive, unsustainable burden on every single developer out there. This flaw wasn't just some abstract idea. It showed up as a trio of recurring nightmares for developers. 3 distinct types of memory bugs that could crash systems, leak sensitive data, and basically roll out the red carpet for attackers. Okay, so curse number 1 is the buffer overflow. The easiest way to think about it is like pouring a full 12 ounces of water into an 8-ounce glass that's sitting right next to an important document. The water doesn't just spill, it ruins the document. In software, this is how attackers could literally overwrite a program's instructions and take control. And that's exactly what happened with the infamous Heartbleed bug. The second curse is the dangling pointer. This one is super sneaky. Imagine you have a key to a P.O. box, but you've stopped renting it. Now, if the post office gives that same box to, say, a bank, your old key could suddenly give you access to all their private mail. In code, this leads to all sorts of unpredictable data corruption and is a massive source of security holes. And the third curse, the data race, is just pure chaos in our modern world of multi-core processors. It's like having 2 accountants trying to update the same bank ledger at the exact same time. One adds a deposit, the other adds withdrawal, but they overwrite each other's work, and the final balance is totally wrong. These bugs are developers' worst nightmare because they're almost impossible to track down and fix. So yeah, for decades, this was just how things were. It was dangerous, but it was the norm. But these 3 curses were finally challenged, not in some high-tech lab or a corporate boardroom, but because of one very frustrated engineer and his daily commute. This timeline really shows how a personal pet peeve for a developer named Graydon Hoare became something huge. The elevator in his building kept crashing, and he knew it was almost certainly because of the very memory bugs we just talked about. That long walk up 21 flights of stairs gave him an idea he worked on as a personal project for 3 whole years before his employer, Mozilla, caught wind of it and saw its incredible potential. This quote just says it all, doesn't it? It's that moment where this abstract, professional anxiety about software being fragile suddenly becomes a very concrete, very personal mission. The problem wasn't just a number in a security report anymore. It was 21 flights of stairs. It was a personal insult to his entire profession. So with Mozilla's support, Hoare's language, which he named Rust, was given a truly monumental task. This wasn't going to be some academic exercise. No, this language was going to be forged in the fire of one of the absolute hardest problems in software engineering. And that task was Project Servo. Mozilla wanted to build a completely new web browser engine, the core part of a browser that actually draws the web pages. Now, you have to understand, this is a monumentally complex job, and Servo had 2 incredibly ambitious goals that, no existing language could really handle. First, Servo had to be fearlessly concurrent, built from day 1 to use all the cores in modern processors for a huge speed boost. And second, it needed to have guaranteed safety, to be immune, by its very design, to all those memory bugs that Mozilla was spending tons of time fixing in Firefox. In other words, it needed to be blazing fast and perfectly safe, the very combination everyone thought was impossible. So the big question is, how did Rust actually do it? How did it break this 50-year compromise? Well, it wasn't magic. It was a set of really elegant ideas, all built on top of one golden rule. And that rule is zero-cost abstractions. Now, that sounds a bit technical, but the idea is actually pretty simple. It means all the complex safety checks happen when the code is compiled, before the program ever runs. It's kind of like an architect using a supercomputer to prove a building is earthquake-proof before they even start construction. The final building isn't weighed down by clunky safety equipment. Its safety is just part of its design. The core idea that makes all this possible is called ownership, and it's governed by these three simple rules. The best way to think about it is like the title to a car. Every single piece of memory has one and only one clear owner. There's never any confusion about who's responsible for it. And when that owner is done, the memory is cleaned up automatically. No manual work, no slow garbage collector. But what if you need to let someone else use your car for a bit? That's where this brilliant idea of borrowing comes in. You can either give out lots of copies of your car keys so people can look at the car, that's an immutable borrow. Or you can give the single master key to one mechanic so they can work on the car, a mutable borrow. And here's the genius part. The compiler enforces that you can never do both at the same time. And just like that, data races become impossible by design. The part of the compiler that enforces all these rules is called the borrow checker. And, okay, when people first start learning Rust, they often feel like they're fighting it. But experienced developers see it completely differently. To them, it's not an adversary. It's like a brilliant, super helpful assistant that checks all your work and finds bugs before they can ever do any damage. So what's been the impact of this whole revolutionary approach? By proving that the impossible was, in fact, possible, Rust didn't just create a new language. It created an entirely new standard for the whole industry. For years and years now, developers have voted Rust the most loved language in the industry's biggest annual survey. Now, that doesn't mean it's the most used, yet, but what it shows is that once developers get past that initial learning curve, they absolutely fall in love with it. They find its guarantees of safety and performance are a total game changer for their productivity. And all that love from developers has translated directly into real-world adoption by the biggest tech companies on the planet. We're talking AWS and Microsoft rewriting their core cloud infrastructure in Rust. It's the first new language accepted into the Linux kernel since C was created, and it powers massive services that you probably use every day, like Discord and Dropbox. Basically, wherever performance and safety are absolutely non-negotiable, you'll find Rust. So when you boil it all down, what Rust did was prove that the 50-year compromise was a false choice all along. It showed the entire world that we no longer have to sacrifice safety to get speed. We can have both. And now that we know that, we should demand both. The story of Rust is just such a powerful reminder that even the most fundamental, long-held beliefs in any industry can be challenged and broken. It all started with one person's frustration, and it ended by elevating the standards of reliability and security for our entire digital world. It just makes you wonder, what other unbreakable rules are out there just waiting for the right spark?